Task number 6, the finger of this. Andrei Vladyshenko, first year School of Radio Engineering and Computer Technology student.
And I'm Maxim Klemenov, first year School of Applied and Fundamental Physics.
The task was about forming special stalactites in the sea. Under some conditions, special stalactites called brinicles can be formed in the sea. Our task was to study this effect and study about their length and maximal size.
Okay, so firstly, we'll give some general information about the effect observed and qualitative explanation. Then we'll describe our laboratory analogy of the experiment, and finally tell some words about heat conductivity approach that we used in our work.
When sea water freezes, a special system of channels can be formed into the ice. You can see this system on the picture. And when this system opens out, the brinicle can be formed, and the water in these channels is about minus 35, minus 40 degrees Celsius.
So, and this system tends to reach thermodynamical equilibrium and warm up the cold brine that flows from the top to the bottom of the to the bottom. Yes, and as the seawater is at its transit point, the least way it can release energy is just to freeze around the flow, and that's the way the brinicle forms. It's also essential to pinpoint that inner boundary also moves, and it becomes wider not only from the outside but also inside.
These brinicles can be observed in nature, but there is some problems because there is 100 liters of cold brine is needed to form one stalactite with the length about 1 meter, and the distance between two big stalactites is about meter. Unfortunately, we can't afford to make such big setup, so we built an analogy effect in our laboratory conditions. We used a special hole to pour cold brine into this hole and to view our stalactite. You can see the first variant of our setup. There is a bottle with LEDs and cameras to observe this effect, and you can see the experiments in the freezer because we need such temperature. This is the last version of our setup. We have main tank with cool brine about -4 degrees Celsius. The funnel on the top, and another reservoir with cold brine. We use pipes and pump to put cold brine into a funnel, and then it goes through the hole to main tank. To keep the level of brine constant, we use extra reservoir to put their waste liquid.
Okay, so here you can see brine formation processes, and there's laminar brine flow inside the left one, and turbulent flow in the right one. So it changed the form of the brinicles. And yes, that's our effect observation.
Of course, we faced to some difficulties. On the left picture, you can see small barnacle which were received from experiment with not cold enough water from the extra tank. And on the right video, you can see the bad quality of video because there was a mix of ice and water which destroy our experiment.
Okay, so now to explain the effect theoretically, we used thermoconductivity theory approach, and inside there flows a brine with temperature Ts. Outside there is water with higher temperature Tw, and temperature of the barnacle is Ti. And if we look at a small cross-sectional area and determine inner and outer radiuses as R1 and R2, we can write Fourier law for that process. And substituting boundary conditions, we get this equation that describes a radial growth of our barnacle. Then vertical growth. For Poiseuille flow, there is a special equation that can be solved with a number of boundary conditions. And we made that boundary conditions. First of all, at the entrance, the brine temperature is constant. Then the heat flux on the fixed Z coordinate is just function of time. Then at the tip, temperature of the brine and temperature of ice equals temperature of water. And finally, stalactite's tip grows as a cylinder of constant cross-sectional area. And all that boundary conditions allowed us to come to a power law of time where L and T are dimensionless variables. But yes, but that's the power law. Also, it was important to understand the dependence of the freezing temperature on salinity. And according to theoretical works, it must be linear. However, it is true only for quite high cold brines. And we worked with much more lower temperatures, and there we find just experimental data and created a square law for that eutectic curve because we couldn't find any theoretical work on that.
So we fitted the parameter T0 and get accuracy about 90%, and it's give us a good communication to theoretical models. And then we use Taylor transformation to main equation, and we received the equation which you can see on the slide, and the last member is neglectedly small. So T0 is also fixed by few constant and depends only from C, which depends from alpha and mu. Alpha is a parameter of percentage of heat is lost in collinear process, and mu is parameter of heat transformation from the entrance of the barnacle to the end of the barnacle. So these parameters are adequate, sorry, and they confirm our model.
And based on the main equations of our model, there was a numerical simulation built, and it fully describes barnacle process growth by its initial diameter, flow rate, and salinities with fitting parameters alpha and mu. So there are two fitting parameters, and both qualitative and quantitative approach saying that inner boundary must grow. And we tried to conduct an experiment on that, and we found that the trend of our diameter growth is goes up, and that also confirmed our theoretical ideas. And with two fitting parameters, this simulation allows us to create models for our experiments, and we can even predict the form and the size of this brine by initial parameters using two fitting parameters, alpha and mu, as I said. And yes, the product is fixed by initial experimental data.
We express our infinite gratitude to all people who helped us to make this report and to set up. And there is our reference list. And thank you for your attention.